Welcome back to G-Fun Facts Online. Today, we are stripping away the surface of our world to look at the engine driving it from beneath. We often think of the ground beneath our feet as solid and static, but if you look at the geological history of Earth, the crust we live on is more like a thin skin floating on a churning, dynamic ocean of rock. Most of the fiery action we hear about happens at the seams, where tectonic plates crash together to build mountains or pull apart to widen oceans. But there is another class of volcanism, a more mysterious and potent force that ignores these boundaries completely. These are hotspots. Imagine a blowtorch held steady beneath a moving sheet of metal. That is essentially what a hotspot is, an anomaly of intense heat that pierces right through the Earth's crust, creating chains of islands, fueling supervolcanoes, and laying down massive flood basalts that have, at times, nearly wiped out life on Earth. Today, we are going to dive deep into the science of hotspot volcanism, based on the pulse of the planet. We are going to cover everything, from the physics of mantle plumes to the forensic evidence hidden in helium atoms. Let's start with the mechanics. How does this actually work? Unlike the friction-driven melting you get at plate boundaries, hotspots are fueled by what we call mantle plumes. These are vast columns of superheated rock, rising all the way from the abyss, specifically from the core mantle boundary, which is nearly 2,900 kilometers, or 1,800 miles beneath us. It is a direct line of communication between the Earth's core and the surface. Now, we have to credit the geophysicist J. Tuzo Wilson for cracking this code back in 1963. He was looking at the Hawaiian Islands and noticed something strange. They are a line, a neat, linear chain, and they get progressively older the further northwest you go. Wilson proposed that the Pacific tectonic plate was moving over a stationary hotspot deep in the mantle, much like a piece of fabric moving over a stationary needle on a sewing machine. The needle stays put, punching holes in the fabric as it moves. In 1971, W. Jason Morgan refined this into the mantle plume theory. He suggested that these plumes have a specific anatomy. When a plume first starts to rise, it has a massive mushroom-shaped head. When this head hits the bottom of the rigid outer shell of the Earth, the lithosphere, it flattens out and melts catastrophically. This creates what we call large igneous provinces, or LIPs, huge, flood-like eruptions. Once that head dissipates, you are left with the tail, a narrow stream of hot material that continues to rise for tens or hundreds of millions of years. This tail is what creates the steady tracks of volcanoes we see on maps today. But here is the physics question. Why does the rock rise? It is thermal buoyancy. The rock in a plume isn't liquid magma yet. It is solid rock that is just much hotter, and therefore less dense than the surrounding mantle. Because it is less dense, it floats upward. It rises slowly, maybe a few centimeters a year. The magic happens when it gets close to the surface. As this solid rock rises, the pressure on it drops. Now usually, pressure holds the crystal lattice of rock together. But when that pressure is removed, while the temperature stays high, the rock undergoes what we call adiabatic decompression melting. It flashes into liquid magma, burns through the crust, and erupts. There is a minority view called plate theory that suggests these are just cracks in the crust, but as we will see later, the chemical evidence heavily favors the deep mantle plume model. Let's take a tour of what these plumes create on the surface, because the result depends entirely on where the blowtorch hits. The classic example is, of course, Hawaii. The Hawaiian Emperor Seamount Chain stretches over 6,000 kilometers. It is a geological archive recording 80 million years of plate motion. Right now, the big island of Hawaii is sitting directly over the hotspot, which is why Mauna Loa and Kilauea are so active. As you move northwest to Maui, Oahu, and Kauai, the islands get older, colder, and more eroded. There is a famous feature in this chain called the bend. About 47 million years ago, the straight line of islands takes a sharp 60-degree turn. For a long time, we thought the Pacific plate changed direction, but new research suggests the plate didn't just turn. The hotspot itself might have drifted in the mantle wind before stabilizing, and the factory is still running. South of the Big Island, there is a submarine volcano called Loehi. It is growing 1,000 meters beneath the waves. Give it 10,000 to 100,000 years, and it will be the newest island in the chain. Now, take that same blowtorch and put it under a thick continental plate, and you get a monster. You get Yellowstone. The Yellowstone hotspot has burned a path across North America, creating the Snake River Plain in Idaho before landing in Wyoming. The difference here is chemistry. When you melt continental crust, you get sticky, silica-rich, rhyolitic magma. This stuff traps gas like a shaken soda bottle. It doesn't flow, it explodes. That is why Yellowstone is a supervolcano. We can trace a trail of dead supervolcanoes stretching southwest from the current park, marking where the continent slid over the plume. Today, that heat powers the geysers and hot springs, and while the media loves the doomsday eruption scenario, the most likely future activity is actually hydrothermal explosions, or small lava flows. Then there is Iceland. This is a unique laboratory because Iceland sits on top of a hotspot and a divergent plate boundary, the mid-Atlantic ridge, at the same time. Usually, the ridge is underwater, but the extra heat from the plume underneath Iceland creates excess melting, making the crust there over 40 kilometers thick. It literally props the island up above sea level. This combination makes Icelandic volcanoes incredibly dangerous in terms of climate. Take the Lake eruption of 1783. It didn't just spew lava. It released enough sulfur dioxide to cool the entire northern hemisphere, causing crop failures and famine across Europe. It shows how a geological event can ripple through human history. And we can't forget the Galapagos. Located on the Nazca Plate, this hotspot interacts with a spreading center in a complex dance, creating a scattered archipelago rather than a neat line. The isolation of these volcanic islands created a crucible for life, inspiring Charles Darwin's theory of natural selection. But how do we know all this? We can't drill to the core. We have to use forensics. The strongest evidence is the DNA of the lava, specifically helium. Helium comes in two main isotopes, helium-4 and helium-3. Helium-4 is boring. It is produced constantly by radioactive decay in the crust. But helium-3 is primordial. It was trapped inside the Earth when the planet formed 4.5 billion years ago. Most of the upper mantle has lost its helium-3 over billions of years of eruptions, but the lava from hotspots often has extremely high ratios of helium-3. This is the smoking gun. It tells us that this magma is coming from a pristine, isolated reservoir deep in the lower mantle that hasn't mixed with the upper layers since the dawn of the planet. It is a time capsule from the birth of Earth. We also use seismic tomography, which is like a CT scan for the planet using earthquake waves. This technology has revealed two massive continent-sized blobs of dense, hot rock sitting at the bottom of the mantle, one under Africa and one under the Pacific. Scientists call these large low shear velocity provinces, or LLSVPs. It turns out, nearly all the major hotspots on Earth can be traced back to the edges of these blobs. Plumes seem to rise from the margins of these deep thermochemical piles, like smoke rising from a chimney. However, this geological wonder has a dark side. Remember the mushroom head of the plume? When that head hits the surface, it creates a large igneous province. These events have driven mass extinctions. About 66 million years ago, the Reunion hotspot, which is now under Reunion Island, was under India. It unleashed the Deccan traps, covering 500,000 square kilometers in lava. The gases released stressed global ecosystems so badly that when the Chicxulub asteroid hit, the dinosaurs didn't stand a chance. Even worse was the Siberian traps event 252 million years ago. A massive plume beneath Siberia released trillions of tons of carbon and methane. It warmed the planet and acidified the oceans, triggering the end Permian mass extinction, also known as the Great Dying. 96% of marine species vanished. It was the closest life on Earth has ever come to being completely extinguished. Yet, we must balance this destruction with the gifts of fire. Hotspots are vital for life. Look at Iceland again. They generate over 25% of their electricity and 90% of their home heating from geothermal energy derived directly from their hotspot. It is clean, renewable, and virtually limitless. Then there is the soil. Volcanic ash and basalt break down into some of the most fertile soils on the planet, rich in iron, magnesium, and potassium. This supports lush rainforests in Hawaii and feeds millions of people near volcanoes like Mount Etna. And biologically, these remote islands act as blank slates. When species arrive at a place like Hawaii or the Galapagos, they undergo adaptive radiation, evolving into unique forms found nowhere else. The biological novelty of our planet is driven in large part by this geological isolation. So in conclusion, hotspot volcanism is more than just a cool fact about volcanoes. It is a fundamental process of our living planet. It recycles material from the deep Earth to the atmosphere, it regulates the long-term carbon cycle, and it creates new land for life to colonize. From the microscopic helium atoms trapped in lava to the massive provinces that have dictated the fate of species, hotspots remind us that the Earth is connected from its core to its crust. As we continue to monitor these sleeping giants with satellites and seismometers, we gain not only a better understanding of natural hazards, but also a deeper appreciation for the fiery engine that drives our world. Thanks for listening to G Fun Facts Online, and we will catch you in the next deep dive.